The following program is part of Cable in the Classroom, a free service of the cable telecommunications industry and your local cable company.
ESPN is proud of the many awards that SportsFigures has received, and we want to thank all the great athletes who have donated their time to help you put your brain in the game. Now let's go out on the water to see pro water skier Ronnie Barton take us in circles at the end of her tow rope.
And so Ronnie Barton takes it all the way home here on the SportsFigures Classic Slaloming Championship. Okay, Ronnie, it seemed like you were having a little trouble out there today. You kept zigzagging all over the place, but you managed to stay up.
Well, it's slalom. You're supposed to zigzag.
Oh, is that what all those little balls are for you to go around?
Yeah.
Now, there seemed to be a trouble with the rope. It seemed to get shorter every round. Did it keep breaking?
No. After you successfully complete a pass, you stop on the end, and the judge shortens the rope to make it more difficult.
Oh, wow.
Have you ever covered water skiing before?
Well, actually, science is more my thing.
In the old days, people used to water ski like this. Nowadays, they water ski like this.
If you've ever water skied or watched someone water ski, you might have noticed this.
See, Ronnie caught up with the boat. That should be impossible, right? I mean, the boat is what's pulling her. To catch up like that, she'd have to be going faster than the boat.
Weird, right? How can a water skier get going faster than the boat that's throwing them? And how much faster can she go?
Hey, Ronnie, could you give us some of the basics of slalom? How does it work?
Okay, well, the course is made up of entrance gates, exit gates, and 6 buoys. The skier has to go through the gates, around all 6 buoys, and out the exit gates.
Sometimes it seems that you're going faster than the boat. Is that an optical illusion?
No, in fact, when we're cutting through the wakes, we can almost double our speed. And the speed that we generate going through the wakes gives us enough speed up on the buoy that we're actually free from the pull of the boat.
The boat is traveling at a constant velocity. We know that when Ronnie is directly behind the boat and not swinging out to either side, she's in a state of equilibrium. That means that all the forces and torques acting on her add up to 0. There's no net force. And we know this because there's no acceleration. Okay, guys, so what does it mean that there's no acceleration? A skier is moving.
Something can be moving without accelerating.
Acceleration means a change in speed or direction.
At a constant speed and just going straight behind the boat, the skier's not accelerating.
The only time there's acceleration is when the forces don't add up to 0. They're out of balance.
Let's look at our force problem from directly above. We'll put it on the IJ axis because we're working with force vectors. Everything's in equilibrium or balance. Let's say the tow rope exerts a force of 0I plus 50J on the skier, and the water exerts a force of 0I plus negative 50J. 50 plus negative 50 equals 0. With the boat traveling at a constant velocity, the forces cancel out and the skier doesn't accelerate. By leaning back and turning, the skier digs the ski deeper into the water, and the water creates a greater force against the ski. Now she's traveling sideways in relation to the boat. Now there's a greater force from the water and a greater force from the rope. Let's say 0I plus 80J. The water's force has to equal that. But the ski is at an angle to the tow rope force, right? So to figure it out, we have to break the water's vector down into its vertical and horizontal components. The water's force vector will be 40I negative 70J.
I thought you said that it had to equal the force from the tow rope.
But you can't add them that way. Because you're making a triangle, you have to use the Pythagorean theorem. Our angled force is the resultant vector of our horizontal and vertical forces. All together they form a right triangle, with the resultant as the hypotenuse. So we have to use c squared equals a squared plus b squared. For our a side, we get 40I, and for our b side, we get negative 70J. And solving for them, we can get about 80 as our resultant. Now we can add the I and j components of our vectors.
Okay, we have the rope pulling with a vector of 0i plus 80j, and the water's exerting a force on the ski of 40i plus negative 70j. They're different, right?
Well, the water's exerting a force toward the outside. The rope doesn't exert any force against the I-axis to balance it out.
And there's an imbalance on the j-axis of net force toward the boat. And when you have forces out of balance,
you get an acceleration.
Before, when we added our vectors, we got a sum of 0, right? Everything was in balance. Now, when we add our vectors, the sum isn't 0. They don't balance out. We get 40i plus 10j. There's a net force on the I and j axes. That means toward the boat and to the outside. The force vector constantly changes as the skier comes up even with the boat. Watch the rope's vector. Eventually, there's no net force in toward the boat.
With no force from the boat, the ski can't push back against the water with an opposite force. Not only is that force what accelerates her, it's what keeps her up. Sorry, Ronnie. So now we know why a water skier accelerates. But how much can they accelerate?
Well, speed is a measure of distance over time, so we need to figure out how far a skier is going and how long a time.
Okay, so first we need to figure out a water skier's path, and then how long it is.
A water skier is just like the ball at the end of a string. Ronnie is describing the arc of a circle in the water, right? And just like the ball at the end of this string, the rope length stays constant and forms the radius of the circle. To find her speed, we need distance and time. We need to find out the dimensions of the circle in order to find out the distance Ronnie's traveled. Let's use the first round rope length of 75 feet.
This is the total circle that our skier could make. And we know the total distance around a circle is called the circumference. Now we're only interested in this part of the circle here, where the skier accelerates. So to find that distance is really simple. We just take our formula for circumference, 2 times pi times radius, and then divide by 4. The radius of our circle is the length of the rope, 75 feet. So we just multiply 2 times pi, 3.14, times 75. And we get a total circumference of 471 feet. Now we take 1/4 of our circle, divide by 4, and get about 118 feet that the skier travels. Because speed is about distance and time, we need to find out how long it takes Ronnie to go this distance. And we can do that really easily by counting video frames. Video records at 30 frames a second, so all we have to do is count the number of frames and divide by 30. It only takes 53 frames for Ronnie to reach the center of the wake. Let's call that 1.75 seconds. Okay, so now we have the distance and the time. What's next?
Well, now we can find the speed, the velocity.
The velocity equals distance divided by time.
How long it takes you to go a distance.
Okay, that makes sense. To get the skier's average velocity, we just divide distance by time. 118 feet divided by 1.75 seconds equals 67 feet per second. 67 feet per second? That's pretty fast. That's 45 miles per hour. Hey, that was a stop sign, buddy. 67 feet per second is Ronnie's average speed over this distance. She'll be going slower at the start and faster when she hits the wake.
The towboat stays at a constant speed of 34 miles per hour. That's about 50 feet per second.
Ronnie has an average speed of 45 miles per hour, 67 feet per second. We could figure out what percentage of the boat's speed that is by just dividing. And we find that Ronnie gets going around 75% faster than the boat.
But sometimes I get going way faster than 45 miles an hour.
Yeah, that's just your average speed over that distance. When you hit the wake, you could be going 55 to 60 miles per hour.
So we have why a skier accelerates, how fast they get going, and how much they accelerate. Woo! Who thought water skiing would be so complicated? Or so wet.
Okay, guys, that was a lot. So what did we learn?
That a water skier accelerates because the forces are out of balance, because they dig their ski into the water. Yeah, and whenever forces are out of balance, something accelerates.
And acceleration is the change in speed or direction.
And you can figure out with force vectors.
We learned that you can find an object's velocity by dividing distance by time.
Right.
Well, that's it. We'd like to thank Ronnie Barton and our students, Sarah, Matt, Christina, and Heidi, for helping us out here today on ESPN Sports Figures Water Skiing in Circle.
We hope you've enjoyed ESPN Sports Figures. It's always smart to put your brain in the game. I'm Reese Davis. We'll see you next time on Sports Figures.
ESPN Sports Figures is presented commercial-free for educators to tape and use in the classroom.
For a free teacher's curriculum, to order the Sports Figures series, or if you have questions or comments,
Visit our website at espnsportsfigures.com.
you can also call 1-800-565-0452.
This has been a presentation of ESPN, the worldwide leader in sports. For more, log on to espn.com.
Sports Figures. Put your brain in the game.
The preceding program is part of Cable in the Classroom, a free service of the cable telecommunications industry and your local cable company.